Welcome back to this video tutorial. We can discuss about the instruction sets of 8086. We have different classifications like data copy or data transfer instructions, arithmetic and logic instruction, branching instruction, looping instructions, machine control instructions, flag manipulation instructions, shift and rotate instruction, string instructions. Okay, so we can consider one after another, and in this video we can discuss about the data copy or data transfer instructions. So the first one in this category is the move instruction, which transfer data from one register or from a memory location to another register or memory location. And the source may be any one of the segment register or general purpose register or special purpose register or some memory locations. And the destination may be another register or memory location on. Okay, so immediate data is not permitted in case of destination. Some examples: move AX, 5000H, send immediate data transfer, transferring this value 5000 to AX register. And this indicate a register mode of transferring, that is move content of register BX. The value present in BX is loaded into or moved into register AX. Here indirect transferring, that is SI is a source index register pointing to some memory location from where fetch the value and moved into AX register. This is direct transferring, that is from address location 2000 we fetch the value and load into register AX. Move AX, 50HBX, that is base plus relative with displacement, that is we need to add the content of this base register with the displacement value this 50, and that location gives the value that we want to load into register AX. Next, direct loading of segment register with immediate data is not permitted. This is an exception. In case of segment register, we can't load immediate data. So move DS, 5000H, this is an invalid case. We can't load immediate data to segment registers like data segment, code segment, etc. So instead of this, we can follow these sequence of instructions which will help us to transfer data to segment registers, like move AX, 5000H. Move this value first to this accumulator register, and from the accumulator register we can load into the segment register. This is a valid case. But the source and destination operands cannot be memory location. In case of move instruction, both the source and destination cannot be both the same, they cannot be the memory locations. And next about the push instruction, which pushes the content of the specified register or memory location onto the stack. Stack pointer is decremented by 2 after each execution of instruction. Higher byte is pushed first and then the lower byte. Okay, so while pushing we need to push the higher byte of data first to the stack top and then decrement the stack top by 1, and again we need to push the second byte, the lower byte, to the stack top. Register SS indicate the stack address, static address of the stack segment, and SP point to the stack top. So consider one example for this push instruction. Push AX means we want to push the content of this 16-bit AX accumulator register. Assume the content of AX as 5522H, SS as 2000H, and stack pointer as FFFH. So this is the accumulator register content. This higher byte with 55 and lower byte AL position with 22. First we want to push the higher byte data. Now suppose the stack pointer is pointing here, so decrement by 1 and point to this location and load here the higher byte of AX55. Then again decrement by 1 and load this lower byte value there. So after executing this push operation, the stack pointer decrement 2 times or decrement 2 bytes and pointing to the new location. This is because the stack is growing in the opposite direction of its address value. That is why while pushing, we need to perform this decrement operation in order to get the new free location. So another example for the push content of 5000H. That means at a memory location 50000, we need to fetch the value and we need to store into the stack segment. First push the value from 5001 onto the stack top, then decrement by 1. Next push the value from 5000. That is first higher byte we need to push and then lower byte. Next is about the POP instruction. Load the specified register or memory location with the content specified by stack segment and stack pointer. Load register or memory with the stack top value. Okay, for example, POP AX, SS with 20000H, SP with FFFE. Okay, so AX look like this, AH with 50, AL with 21. So for pushing, for popping, we need to perform pop operation here. That means we need to take bytes from the stack and load into this AX register. That is the working of this pop instruction. Fetch from or pop from the stack and load it into AX register. Suppose AX, whatever content may be present here in the AX register, after pop instruction execution, it gets loaded with the new value from the stack top. So while popping, first pop this to 1, which is present in the stack top and is loaded into the lower byte of this AX register. Then increment by 1 and pointing to the next location and pop the next byte, and this 50 is loaded into the higher byte of AX register. While performing this popping, first first fetch from the stack top and load it into lower byte and increment by 1 and fetch value from the stack top and load it into the higher byte of AX register. But in case of push, first decrement the pointer by 1 on the stack and push the higher byte of this register to the stack. Then again decrement the stack pointer by 1, then load this lower byte of this AX register to the stack top. Okay. Next is about an exchange instruction. This exchange indicated by XCHG used for exchanging data. Exchange the content of 2 memory location is not permitted. So immediate data is also not permitted in case of exchange instruction. This is used just for exchanging value between source and destination, but the exception is exchange the content of 2 memory location. If both source and destination are of memory location, this is not used in case of exchange instruction, and also immediate data is not permitted in case of exchange. So here it is an example: exchange content of 5000H, AX. Content of AX is loaded into location 5000 and the current content of 5000 is loaded back into AX. So whatever value present in this location, now it available in AX register, and whatever value was present in AX, it is now available in this particular memory location. Next is about the input port reading operation, which is represented by using IN, input port reading. AL and AX are the allowed destination for 8 and 16-bit input operation. The only permitted destination for this input reading is AL or AX. DX is the register which can implicitly carry the port address. We can use this DX register in case of inputting and outputting in order to represent the port address implicitly. Okay, so consider this example. In AL, 03H, what is the meaning? Read data from the input port whose address is 03 and store the content available from that port to register AL. A single byte of information from the port 03 is loaded into register AL. Next, move dx comma 0800h and in ax comma dx. Here, this dx register is implicitly used for representing the port address. So, dx hold this port address 0800 while executing this move instruction, and after that we can call this in ax comma dx. That means dx now hold the port address which is completed by this move instruction. So from that port address we can load the value from that load to register AX. So here DX is the register which is implicitly used for storing the port address, and AL and AX registers are used as destination in case of inputting. Similarly, we have the output instruction, writing to an output port using the instruction out. Address to the output may be specified in the instruction directly or implicitly using DS register. The port address can be directly specified or you can implicitly specify using DX register. Register AL and AX are allowed source operands for 8-bit and 16-bit operations. Out 03H comma AL is an example. Out 03H comma AL. Send the data available in AL register to the port whose address is 03H, which is directly available in this instruction. Okay, for implicitly using the DS register as the port address, follow these two steps. Move DX comma 0300H. 16-bit port address taken in DX register first, then perform this out instruction, that is out dx comma AX. Content of AX is written to a port address output port whose address is now available in this DX register. Okay, so DX register is implicitly used for storing the address information of different output port or input port. Next is an instruction XLATE. This is the short form of translate, and is mainly used for code conversion. Because sometimes we need to convert the hexadecimal representation into 7-segment display format in order to display the resultant value on a screen. So we need similar code conversions. So in order to perform this conversion, we can use this XLATE instruction. Next is about LEA, load effective address. Load the effective address or the offset address formed by destination operand into a specified source register. Okay, so for getting the offset address of certain memory label to some destination register, that is LEA BX comma ADR. ADR is a memory label, so we can find the offset value of that particular label and load into BX register. LEA SI comma ADR content of BX. Offset of the label ADR will be added to the content of BX register to form the effective address and will be loaded into SI. The offset address of ADR is added with the content of BX register and generate the effective address. And that address is loaded into SI, source index register. Next is about LDS or LES, load data segment register or load effective segment register. Load the DS or ES register and the specified destination register in the instruction with the content of memory location specified as the source in the instruction. LDX BX, 5000H. What's the meaning? From the memory, from address location of 5000, we need to fetch 2 consecutive byte and load into BX register first. So 01 fetch first, load into the lower byte of BX, and 22 is fetched second, load into BX register as a higher byte. then fetch 2 3, which is loaded into DS or ES. If this instruction is executing, so here it is the data segment register. So the third byte starting from this 5000 address location, the third byte, this is the third byte which is loaded into the lower byte of DS register, and the fourth byte is loaded into the higher byte of DS register. If suppose we are executing this particular instruction, then first load 2 bytes to the BX register, then load next 2 bytes to the ES register, extra segment register. Okay, next is about LAHF. LAHF means load AH from lower byte of the flag register. AH is the higher byte of AX accumulator. So LAHF means load AH from the lower byte of the flag register. 8086 is with 16-bit flag register in which 9 bits are active in case of 8086. Anyways, the lower byte of the flag register is loaded into AH of higher byte of AX register. That is actually the status flag bits information loaded into the AH. Okay, used to observe the status of all condition code flags at a time. This LAHF is usually performed in order to get the status information. Okay, and SAHF store AH content to the lower byte of the flag register. LAHF is load instruction and SAHF is the store instruction. Store content of AH to the lower byte of flag register. Set or reset the condition code flags. This set AH or store AHFs is used for setting or resetting conditional code flags. Okay. In the lower byte of the flag register, depending upon the corresponding bit position in AH. Okay, so here we can load AH with lower byte of flag, and here we can store the content of AH to the lower byte of flag. Lower byte of flag register actually indicate the status information of the processor or the status information of the previous instruction execution. Next is about PUSHF. Push flag to the stack. A6 is with 16-bit flag register. Among 9 bits are active, but we can push as a whole the 16-bit into the stack. The higher byte first, then the lower byte. First upper byte and then the lower byte is pushed onto stack using this PUSHF, push flag register. POPF means pop the flag register from the stack. First pop the stack top and is loaded into the lower byte of the stack, lower byte of the flag. Then increment the stack top by 1 and pointing to the next location and fetch the value from that location and load it into the higher byte of the flag. Okay. So these are different instructions available in case of data transfer or data copy instructions. Okay, so in the next video we can discuss about various arithmetic instructions. Thank you.